Hello and welcome back. So it's been quite a while since I recorded a video. Um, 2020 has been a busy and disruptive year for me so far, as I'm sure has been for a lot of you viewers. Um, I wanted to continue recording some admin of code solutions. Maybe it's a little bit weird since we're 6 months out from the competition now. But I thought it might be nice just to see how some of these problems are solved in APL, because I think some of the later problems especially demonstrate some strengths of APL and lend themselves nicely to some array-based solutions. I am most likely going to be skipping over the int code questions. So I think it's odd days, day 9, day 11, day 13. I have solutions to some of those on my GitHub if you want to check those out. I just don't want to, for the most part, the encode questions are a little more tedious for me personally, and they're not as fun as some of the more open-ended questions, especially with APL, because the open-ended ones, as I said previously, have nice array-based solutions a lot of the time. So what we're going to be looking at today is problem 10. Just to give you a quick refresher, problem 10, we basically have a map of asteroids, and we're going to be doing some coordinate math on that map to try and figure out some various things. So let's take a look at the map first. Text. This is our problem input. So each pound sign here represents an asteroid, and then a dot is just empty space. And I believe our first question says we need to figure out which asteroid would be the best place to build a new monitoring station. Can detect any asteroid to which it has direct line of sight. So I'm guessing like you can draw a vector from a pound sign to another pound sign, and there cannot be another asteroid directly between them, right? So can be at any angle. Best location is the asteroid that can detect the largest number of other asteroids. Okay, fair enough. How many other asteroids can be detected from that ideal location? Cool, let's take a look. By the way, this is not I'm not even pretending this is a live solution. I had a solution for this back when the contest is running. It's been on my GitHub for a while. Again, I'm just making a video to walk through the solution because I think it's kind of cool. So if we want to get the coordinates of all these different asteroids, we can, as usual, we can ingit p10.text. One disclose will give us the rows. We can mix those. Yep. And then if we just want the coordinates of the asteroids, we can say, give me pound sign equals where. And you guys probably know the drill by now. This will give you a Boolean matrix, and then where will tell you the coordinates of the ones. Now, something important to note here is that our coordinates are going to be backwards from what the problem expects. So in APL, we operate, our coordinates here are going to be in row major order. So you can see we have an asteroid here at 1, 2. And that means, if we go down to row 1, one other thing before I forget, sorry. Let me show you the problem spec. So the problem spec, there's a couple things going on with these coordinates. So the problem spec says top left corner is 0, 0, and the position immediately to its right is 1, 0. So before anything else, we should set IO to 0. By default, APL uses 1-based indexing, but this problem calls for 0-based indexing, so we'll switch that. And then, yeah, so if we look here, we're now in zero-based indexing, and we say, okay, we have an asteroid at 0, 1. And yeah, so at row 0, coordinate 1, we have an asteroid. Makes sense. Same for like 0, 4. Yep. So now the problem is that this calls for xy coordinates, where x is the distance from the left edge, and y is the distance from the top edge. And you can see here that we're sort of operating under y-x coordinates, where the first number is the distance from the top, and the second number is the distance from the left edge. I'm not going to fix this right now. So if we wanted to, we could do something like, for each reverse, and that would give us sort of the coordinates that the problem's calling for. I'm not going to fix this right now for reasons that will become apparent later. But just keep that in the back of your mind, that our coordinates are sort of backwards for right now. So we'll assign this to P, and P are the coordinates of our asteroids in the input. Okay, great. So the question asks us to find the number of asteroids that are visible from a particular location. So the first thing that we want to do, I think, is we want to get the relative coordinates for each asteroid. So like given, our first asteroid here at 1, 0, what are the relative coordinates of all the other asteroids? And same for 4, 0, 7, 0, etc. Geez. Yeah, whatever. So fix that. So what we can do is we can take the outer product minus of P. And what this is going to do is it'll take each element of P, which is going to be a coordinate pair, and it will subtract them against all of the elements in P, including itself. So if we look at this, we can see we have zeros across the diagonal here, which makes sense because an element minus itself is going to be 0. But then our other elements are going to be relative coordinates. Hopefully that makes sense. So yeah, so in order to get the relative coordinate of 1, 0 to 10, 0, we'll just subtract 1, 0, and we'll say, yeah, this asteroid is off by 9, right? Now the problem with this matrix is that we don't want the 0, 0s in there because it doesn't really make sense to we're not interested in comparing an asteroid to itself. So one way that we can do this is we can say rank 1, which means that we're going to be operating on the rows. I explained the rank operator in day 8, I think, so you can go back and take a look. And we'll say we'll take omega without the enclose 0, 0. This is just going to strip those 0, 0 coordinate pairs out. And it's a little bit slow to come up here, not because, and I've mentioned this in previous videos as well, but it's not because the computation is taking a long time. It's just that it's feeding a ton of data back to the interpreter, and it just takes time to render. So, okay, cool. So the 0, 0s are out. And now, okay, so we can analyze each row. Each row represents the relative coordinates of all the asteroids relative to a particular other asteroid. But the problem is, so you can see here in the problem spec, it says there cannot be another asteroid exactly between them. So in order to eliminate some of these coordinates, well, yeah, I mean, that's what we want to do. We want to eliminate some of these coordinates so that we're only getting a handful of these. Like, we don't want the asteroids that are blocked by an asteroid directly in front of it. So what does that mean? Well, you can imagine, like, if we had, let's say that we had an asteroid at 2,4, and an asteroid at 4,8. These two coordinates, we would only want them to be counted once. Because if you construct a line from 0, 0, so for each one of these rows, we're sort of treating the asteroid as being at the origin on the coordinate plane, or 0, 0. That's what I mean by relative coordinates. If we construct a line from 0, 0 to 2, 4, that line will also intersect with 4, 8. So you can think about it like this asteroid at 2, 4 is blocking us from seeing the asteroid at 4, 8. So we don't want to count this one. So how do we get around that? There are a couple different ways to do this. What I ended up doing is I tried to reduce all the coordinates to essentially like simplified fractions. What do I mean by that? Well, so APL has this, I'll just show it here, this logical OR. And so OR works as you'd expect on Boolean arrays. But if you give it non-Boolean arrays, meaning numbers, it will tell you what the greatest common divisor is. So if we look at, let's say that we look at the greatest common divisor between 4 and 8. Well, it's going to be 4, right? That makes sense. 4 goes evenly into 4, resulting in 1, and goes into 8 twice, resulting in 2. The greatest common divisor between 2 and 4 is 2, which also makes sense. Like it goes into 2 once, which gives you 1, and it goes into 4 twice, which gives you 2. So what if we basically say, hey, can you find me the greatest common divisor and then actually divide that input by that divisor? That's what this train does. So it reduces to find the greatest common divisor, and then it just says take the right argument and divide by that. Right, so that gives us 1, 2 for 2, 4, which makes sense. And it also gives us 1, 2 for 4, 8. So imagine that we reduced this entire matrix that we just built. We apply this for each cell. Right? Now you can see that there's a lot of common elements. A lot of these got reduced out. Cool. So now what? Now we can operate on each row, because let's take a look at the shape of this matrix. So the shape of this is 320, 319. So 320, if I just look at how many asteroids we're dealing with in total, we have 320 asteroids. And what the shape is saying is that each row represents a single asteroid. And then the 319 is basically, hey, these are the relative coordinates to every other asteroid, including myself. So that's why this isn't 320, 320. If you just take the shape of this before we pulled out the 0, 0s, then this will be 320, 320. So if you look at this shape, if we want to evaluate all the asteroids, we can look at all the rows. And for each row, now that we've performed this reduction, we want to find the number of unique values. And that will tell you how many unique asteroids you can see from that particular point, not counting asteroids that are blocked by asteroids further in. So because we're operating on rows again, we'll do rank 1. And then, so we want unique, right? That's, where is it? This guy. So this will just pull out all the unique elements in the list, and we want the length of that count. And this vector will tell us how many unique asteroids for each row we can see. And if we want the maximum number of asteroids that we can see from any point, we just take the maximum of this list, and that gives us 276. That is indeed the answer. So yeah, you can see, like, so for APL, basically, we're operating, we generated a giant matrix here, and then we're just operating on the rows. We perform reduction on each cell, and then again operating on rows, we get the unique elements and just count how many there are. And taking the maximum of those counts gives us the answer. So this is kind of a cool, roughly array-based solution. And it's nice that, we have built-ins for greatest common divisor and so forth. Makes it a little easier. Okay, so what are we looking at in part 2? Part 2, we are dealing with a giant laser. And if multiple asteroids are exactly in line with the station and the laser only has enough power to vaporize one of them, okay. That can be detected, can be vaporized, etc., etc. But it won't be vaporized until the laser has returned to the same position by rotating a full 360 degrees. Okay. And this is important. So the laser starts by pointing up and always rotates clockwise. So basically we're imagining, like, hey, now that we've identified our monitoring station, or like our target asteroid, we're going to plant a giant laser on there. We're going to point it due north or up, and we're going to spin it clockwise. It's going to take out a handful of asteroids on each rotation. It's not going to eliminate all of them, because some asteroids are going to be hidden behind other asteroids. And the goal of this problem is to determine what the 200th asteroid to be vaporized is. And then, we do some math on the coordinates to get the final answer. So when I first read this problem, I thought about it a bit, but then I eventually decided that translating our relative coordinates to polar coordinates would be a good start. So if you don't know what polar coordinates are, I just have the Wikipedia article here. And whereas Cartesian coordinates are just xy points, like how far away is it from the x-axis, how far away is it from the y-axis. Polar coordinates are, again, two numbers, but the numbers are the length from the origin, so how far away it is in terms of like a straight line, and then an angle. And for polar coordinates, the angle is going to be measured from the positive x-axis here. You can see the picture. So I think the basic idea here is that we are going to we're going to take the polar coordinates of all of our relative coordinates. Now let's back up, because we only have one set of relative coordinates that we care about. So okay, so the max here is 276. In order to actually get the list of relative coordinates for that target asteroid, we can find the index of the maximum here, 205. And if we go back here before we did any reduction or these other modifications, we can take index 205. And that'll give us a row. And this row is the relative coordinates for all the asteroids from our target monitoring station. So we can assign this to M for monitoring station. And the idea is going to be we're going to translate all of these relative coordinates to polar coordinates. And asteroids that are in a line together, where one is blocked by the other, they're going to have the same angle when we translate the polar coordinates. So I think the idea here is basically we translate into polar coordinates, we sort all of them based on the angle, right? Meaning that we'll try and sort it so that it's in order as the laser is sort of turning around. I'm moving my hands here. You can't see it, but just imagine. So sorting it by angle sort of puts it in the same order that the laser will hit it as it moves around clockwise. And then if we sort each of those angle groups by length, then that'll make sure that we're only hitting asteroids that are visible to us. And that's, there's some other stuff that we have to do, but that's the basic sort of gist of the solution as of right now. We have a problem though, which is that here the laser starts by pointing up and always rotates clockwise. Whereas in the polar coordinate system, we are starting with the laser, you can imagine that we're pointing a laser to the right and we're moving counterclockwise. So now there is a polar function built into the defense library for Dyalog, sort of like the standard library, I guess. And rather than like trying to modify, the source code here to point right and go counterclockwise, we can do some transposition on our existing coordinates in order to fit into this model. So what would that look like? Like how would we reposition our coordinates so that we get the same result for the laser going, starting pointing to the right and going counterclockwise? Well, the first thing that we could do is we could transpose or flip the XY coordinates. So think about this. Imagine we had a point over here at like -4x plus 4y, something like that. So if we have our laser, coming up here, we would want that same point to be in this quadrant if we're doing the transposition correctly. So if we swap the coordinates for -4 and +4, then we'll get +4x, -4y, right? And that sort of, that at least gets us in the right quadrants. But there's one more step that we have to do. That kind of, you can think of the transposition as solving the positional issue. So, we're pointing, we were pointing north, now we're pointing right. There's another step that we have to do to make up for the rotational aspect, because we want to be going clockwise rather than counterclockwise. And in order to do that, we basically invert all of our coordinates around the y-axis. Let me kind of make this bigger. Yeah, there we go. Yeah, we'll invert all of our coordinates around the y-axis. And we can do that by basically multiplying the y-coordinate by -1. So yeah, so we had -4, 4 over here. If we invert those coordinates, we end up with 4, -4. And then if we invert just the if we invert just the y coordinate, that'll move us up here and right into the path of our laser. I'm not sure if I'm doing a good job of explaining this or not, but this is sort of the path that you want to take. So now remember at the very beginning of the video where I said that our coordinates are backwards? That's actually nice right now, because having our coordinates backwards is exactly what I want. So, we were talking about inverting the x and y coordinates. Well, for us, they're already inverted, so we don't need to do that step. But what we do need to do is we need to let's mix m so we get a nice matrix here, and then we'll take 1, -1 times rank 1, and what this is going to do is it's just going to flip our y coordinates around. So we see 22, 16, 22, 13, etc., etc., and these are now inverted. And then given this, we can set ourselves up. We can import polar from the defens library, and polar expects the coordinate pairs arranged along the first axis. Right now they're arranged along the second, so we'll just we can transpose. Right, so now you can look at each column as a coordinate pair basically, and we can do the polar transformation. And what this means essentially is that our first row is going to be length, and then our second row is going to be the angle. So we can assign these separately if we split the list, and then we assign length, angle. So now L is the length portion of our polar coordinates, and A is the angle portion, which is nice because we're going to be operating on length and angle independently. So let's take a step back here and look at what we've done. We've done some coordinate transpositions to make up for the fact that in the problem the laser is pointing up and moving clockwise. In a polar coordinate system, our origin, or you can think of it as the laser, is pointing right or on the positive x-axis, and it's moving counterclockwise. And now for each point, we have length, which tells us how far away it is from our monitoring station or our target asteroid, and we have angle, which tells you which tells you how far off the asteroid is from the starting point of the laser. The angle is in radians, by the way, so it will range from 0 to 2 pi. So that's why we get these numbers in the 5s or whatever. Okay, great. So what was our plan? Our plan was to group our entries by angle, and then sort by angle, so that everything is. So we have basically a list of coordinates based on when the laser is going to hit them, starting from due north. So the way we can do that is to use the key operator. Whenever you're using the word like group, you want to think key operator. And I've used the key operator quite a bit in earlier videos, so feel free to check those out if you're not familiar with it. And then we can just say, hey, concatenate the angle with an enclosed list of coordinates where that angle occurs. And it'll give us something like this. So we get a list of angles here, And then we have a secondary list, which is the coordinates of the asteroids that lie along that angle. Quick shout out to Dyalog for having float comparison tolerance, which allows us to do things like this pretty nicely. And normally with floating point numbers, you can be off by like 0.00001 or whatever, and they won't group nicely. But Dyalog allows you to do that. Okay, so given this, we can sort by angle, like so, and we put this little semicolon in here because when you're sorting on matrices, we're just supplying coordinates for the rows essentially. Cool. And so we start at 0. Our 0 angle is again going to be when the laser is pointing due north, and then as it's increasing, slowly, it's moving clockwise until we get down here to 6.21, which is close to 2 pi. That's going to be just to the left of where the laser starts. So with everything sorted by angle, we don't really care about the angles themselves anymore. We just want the coordinates. So we can take a right tack reduce, which will just give us this rightmost column here. Okay, cool. Now, the problem is each one of our groups here, everything's sorted by angle. That's great. We also need to sort each one of these groups by length. Because remember, as the laser is going around, it's only going to vaporize the closest asteroid on a particular angle. So in order to sort by length, for each one of these groups, we can apply a function. And we can say, okay, index into length, get the length values for each one. Because remember, these numbers here are indices, essentially. And we started off, we generated the length and the angle vectors, where index 0 into length corresponds with index 0 in angle, and so on and so forth. So if we do this, we're just referencing, hey, for this particular index, well, how far away was that index from our monitoring station? And now we can sort. We can sort, right? And sort is remember that it doesn't, the grade up function doesn't necessarily sort in place. Instead, it gives you a list of indices that would be sorted if you index back into the original list. And that is nice because we can take that list of indices and we can plug it back into our original input, like so. So you can see here, like we had a group of 2, 5, 180. These have changed places now that we sorted them based on length. You can see the same thing here. 8 and 103 have now changed places. All these single elements are going to be exactly the same, which sort of makes sense. Sorting isn't going to change, a single list here. 147 and 73 have changed places, etc., etc. Okay, so we have a list of lists here where the entire thing is sorted by angle. That's great. And then each sublist is sorted by length. And if you imagine what we want to do is we sort of want to go through the list and we want to take the first element from each group, right? So like the laser is pointing north, it's moving clockwise, we zap this 180. That leaves 5 because this is going to be on the same angle. And when the laser comes around the next time, it'll get it. But for right now, we're just zapping 180. We zap 15, 28, 40. All these single ones just get destroyed. We come here, we only zap 103. We want to leave 8. And then same here. 147, we're leaving 73. So how are we going to do this? Like we could, come up with some loop construct and basically keep looping until the list is empty or whatever. We have a nicer solution since we're in APL here. We can say, hey, instead, why don't we try mixing all of these coordinates into a matrix? So what mix will do when presented with a list of lists like this is it will pad out missing elements with a fill element, in this case 0, in order to make the dimensions consistent. So we can tell just from this matrix that basically there is a list somewhere in here that has 6 elements in it, right? That is the maximum length of one of our angle groups. And for groups that have less than 6 elements, we're gonna throw some zeros in there. So now watch this. Now, if we transpose this matrix, now things are looking interesting, right? So if we just go along this first row here, we get the elements that I was talking about earlier. Like we just want 180. We want 15, 28, et cetera, et cetera, et cetera. We just want 103. Not 8 yet, just 103, 42, 146, et cetera, et cetera. And if we go row by row here, we get exactly what we want. So we're just pulling 180. The 5 is there for sort of our next pass. We come here to 103. The 8 is left. Etc. We get to the end of the row. We come back. Now we're hitting the 5. We have all these zeros that we have to deal with, but we can do that, and then we hit the 8. So now, if we ravel this, we're putting it into a big list, sort of row by row. And now we can remove the zeros. So we can say, present me the list without zeros. And this gives us the list of coordinates that our laser will hit in like sorted order. Because we sorted by angle, we sorted all the groups by length, and now we've gone through, and with this transposition, we're taking the first element from each group, then we're coming back and we're hitting other elements in sort of row order here. And by removing the zeros, which were placed there when we did the mix, we're not considering any extraneous elements. Now there's a small problem here, which is if we look at the length of this, we get 318. So recall that we're dealing with 320 asteroids, right? Now one of those 320 is going to be our monitoring station. So we would expect our sorted list of other asteroids to be of length 319, right? We started with 320, we take one away, that's our monitoring station, that leaves us 319. But instead we have 318. What happens? Well, so because we're at index origin 0, this list of coordinates up here has a 0 in it somewhere. And when we removed all the zeros, we took that 0 coordinate out as well. So we basically need a way to remove just the fill elements without removing that 0 coordinate. There's probably a good way to do this, but what I did is I just basically added 1 before we did the mix. Now all of our coordinates are 1 based, and at the end of this, I'm just subtracting 1 to get it back to base. And this way, our 0 coordinate is going to be 1. So when we remove all the other zeros, we're not touching that one. So if we look here, yeah, we have 319. Okay. Now we have a sorted list of all the asteroids that our laser is going to hit. Great. What can we do with this? Well, we can we can basically index back into P. This will give us the coordinates of the asteroids. So we generated a list of sorted coordinates here that the laser is going to hit. Now we've translated them back into the coordinates for the asteroids. We can take the 199th coordinate. Remember, because we're zero-based, we want the 200th asteroid, but we start counting from 0. And we get 2113. Let's disclose this. And this should be the coordinates of the asteroid, the 200th asteroid that the laser will hit. But remember, our coordinates are backwards, which helped us nicely when we were doing our polar conversion. But now we have to convert back. So we'll just reverse here, 1321. And then the instructions call for us to multiply the first number by 100 and add them together. And that gives us 1321, which is the answer here. Now there's some tricky things here that we luckily avoided. So if you remember up here, our index of, basically the index of our monitoring station as it appears in P is 205. So we lucked out that the coordinates of our monitoring station are above 200. Otherwise, when we indexed back into P, like say that this was at coordinate, 100 or something like that, we're going to be off by 1 here because we don't want to count our monitoring station. Like, the laser's on our monitoring station, we're not going to shoot ourselves, right? So one thing you could do here is you could say, hey, give me tell me what our the coordinates of our monitoring station. You can just say, like, you're going to assign that to C or whatever. And then here you could say, oh, well, I actually want, P without C. And I'll give you the same answer. Right? P without C should have length 319. Yeah. And you'll want to do this, if you're following along. If your input puts your monitoring station at less than 200, you have to remember to do this. Yeah, hopefully that makes sense. So just to review, we translate our relative coordinates for our monitoring station into polar coordinates. We have to invert the XY coordinates, which we got for free at the beginning of the video, but it's something you'll have to do if you're following along using a different language or whatever. And then we inverted the Y coordinates by multiplying by -1 here. And that allows us to compensate for the mismatch between the polar coordinate system and the, laser coordinate system. So out of the polar coordinates, we got length and angle. We grouped the list of coordinates by angle. We sorted by angle. For each group, we sorted by length. And then we put it all into a matrix. And by transposing, it allows us to pull everything out in row major order. We eliminate the fill elements. We take our coordinates, we index them back into our asteroid coordinates, and we get the 200th. And that's it. So we didn't have to construct loops, we didn't have to do any of this stuff. We're just operating on the whole list at once. And in my mind, that's a fairly elegant solution. So, thanks for watching. If you're interested in the full code, it is available on my GitHub. I'll put a link in the description. Yeah, I might do a couple more of these. Again, I realize that the competition is obviously done, but I don't know. Some of these are interesting problems, and some of the solutions are, they make good use of APL's array primitives and so forth. So, thanks for watching, and I'll see you next time.